It's a pleasure to introduce Dr. Marcos Lopez de Prado. He is a senior managing director at Guggenheim Partners, where he manages several multi-billion-dollar internal funds. He's a research fellow at Lawrence Berkeley National Laboratory's Computational Research Division, where he conducts unclassified research in the mathematics of large-scale financial problems and supercomputing. He has 18 years of trading and investment management experience at some of the largest corporations. He has received several academic appointments, including postdoctoral research fellow at Harvard University and visiting scientist at Cornell University's Operations Research Department. Dr. Lopez de Prado has a PhD in financial economics and a second PhD in mathematical finance from Complutense University in Madrid. Please help me extend a warm welcome to Dr. Marcos Lopez de Prado.
All right, thank you for having me. Tonight I would like to discuss what are the connections between mathematics and economics. I typically give more of math-oriented presentations, but don't worry, today there will be no math, no formulas anyway. So the idea is, how are these two connected? Why are they connected? Economics is, in fact, one of the most highly mathematical fields of research. When many people think about math, applied math, they typically think about physics, engineering, maybe chemistry, biology. But in fact, a few statistics would lead you to believe and conclude that some of the most applied mathematicians actually work in this field, in finance and economics. Let me give you a few examples. I don't know if you're familiar with the Erdős number, how the Erdős number works. So the Erdős number measures the collaboration distance between any two mathematicians. Paul Erdős is a 20th century mathematician who collaborated with 511 collaborators over his life. And he published around 1,520 papers, something like that, 1,520 papers. So he's the most prolific mathematician in history. He died in the year, I think, 1997. And he's at the center of the collaboration graph. So if you would take all the mathematicians who have published research in history, Paul Erdős would be at the center because of the number of publications and the number of collaborators. So, in fact, so much so that when you take MathSciNet, which is the big catalog of all mathematical publications, around 2/3 of all mathematicians who are in that catalog have a collaboration path to Paul Erdős. The reason I say this is because it is a very good tool to understand how interconnected a field is. And what happens is every single winner of the Fields Medal, which is the equivalent, some people say is equivalent to the Nobel Prize in math, every single of the 56 laureates in history has an Erdős number. And this number among Fields medalists ranges between 2 and 6, with an average of 3.36, meaning that the distance between any of these winners of the Fields Medal and Paul Erdős is only 2 steps in between. There are only 2 individuals in between to form a collaboration map, a collaboration path between these two. So for instance, I have an Erdős number of 2 because I collaborated with Neil Culkin, who is a number theorist, and Neil Culkin collaborated with Paul Erdős. The median is 3 among Fields medalists. Now, in economics, there are 76 Nobel laureates in history. Out of these 76, around 62% of them have an Erdős number, which is enormous, considering that this is not pure math. It's applied math and other things. The range is between 2 and 8. Remember that the range for Fields medalists was between 2 and 6. The average is 4.11 compared to 3.36, and the median is 4. Now, in the case of chemistry, the median, chemistry and medicine and physics, the median is 5. The median is 5. And there are many other ways to argue that, in fact, economics and finance is a highly mathematized field, but this is just one very simple way, and it is just measure the collaboration distance between Nobel Prize winners in economics and the center of the collaboration graph in math. Now the question, is the right math being applied? Yes, math is being applied in economics and finance, but is the math that should be applied? And what I will argue in this presentation is that, in fact, the answer is no. There is a lot of math being applied in finance. Some of this math is useful and interesting, but for the most part, happens to be the wrong math. So if you're familiar with a number of very important subjects, like for instance, statistics, econometrics, essentially most of the tools that are being used from a mathematical perspective are geometry, linear algebra, and calculus. Right? When you think of econometrics textbook, you think of regressions, right? You think of maximum likelihood, and you think about optimizing something, for instance, the square of the sum of the square errors. So there will be some calculus, there will be some linear algebra, there will be some geometry. Now, are these subjects interesting and useful? Definitely, but they are not the only ones. You know, if you study math, geometry and linear algebra and calculus are just 3 subjects. But there are plenty of other subjects that mathematicians get in contact with, and in fact, mathematicians use in the financial markets. I'll retake this point a bit later. So, before we try to understand what kind of math is useful in the financial markets, we need to understand what is special about the financial markets. Well, practitioners face a number of difficulties when they apply math to financial markets. Number one, we cannot repeat experiments. We cannot go to May 6, 2010, the flash crash, and repeat that event in absence of some participants in order to understand what is the proper cause-effect mechanism. We just cannot do that. At Berkeley Lab, where I'm affiliated with, that's a physics laboratory. They can repeat experiments over and over and over and over again, controlling for some conditions, until they understand what is the proper mechanism. But that's not possible in finance or in economics. When we study a financial time series, the only thing we have to our disposal is a single path. We have a single realization of this stochastic process. What does this mean? Is that we need to rely fully on the ergodic properties of that process in order to learn something. That's not the case in other fields. In biology, they have access to plenty of subjects. How is a treatment tested in biology or in medicine? They have access to thousands of subjects, and they can test this treatment with these thousands of subjects. To some of them they will give placebo, to some other they will give different treatments, and they will understand very well what is the proper treatment to an illness. But that's not the case in economics. In economics you have a single chance, always. You can only trade this thing once for this period of time. You cannot go back and say, well, now I will, given the same process, a different path of the same process. No, you will never have access to another path of that process. It will be a different path at a different time point. Number 3, in finance, we have the problem that there is a very low signal-to-noise ratio. Why? Because of competition, right? People make money out of this stuff. As a result, if a signal is powerful, it's doomed to disappear. That's not the case in physics. Think when Newton published his Principia, and the fact that he published his Principia and his laws of his 3 laws in particular, his laws involving gravity, it's not that his publication meant that everybody started to levitate, right? Meaning that the publication of this theory didn't mean that the law ceased to work, But that happens all the time in finance. As soon as you publish a paper with a discovery, what these people are doing is they are just actually making the effect disappear, because everybody will go and apply this methodology and the profits will be arbitraged away. That's why I, in general, think that it's a bad idea when someone publishes a paper with some sort of a strategy, because actually, if anything is guaranteed that the strategy is not going to make money anymore. And number 4, financial markets are complex, adaptive systems. When you try to understand gravity, it's not that gravity is going to alter its behavior in order to become more unpredictable. But that's what happens in the financial markets all the time. When you make money in the financial markets, someone must have lost money, which means that either that person lost his job or has learned a lesson. He's not going to make the same mistake again. So financial markets are adaptive systems. The math we need to use to model financial markets must recognize that fact. Now, finally, think what happens when people try to predict climate or the weather. They use supercomputers, like the supercomputers we have access to at Berkeley Lab. And when you think about it, it's something interesting, because weather forecasting is a significantly simpler problem than forecasting the financial markets, right? Meaning that at least the weather follows some particular physical rules, and it's a phenomenon where the hurricane is not altering its behavior to escape your forecast, right? But that's exactly what happens with the financial market. So why is it that a problem that is much simpler than forecasting financial markets requires so much calculation, so much computing power, and yet most people in finance and economics do not claim that they do not need that computational power? It doesn't make sense. If anything, we would need the largest supercomputers in the financial markets. And in fact, some people have access to some of the largest supercomputers to model financial markets. Now, there are a number, again, econometrics is a very interesting and useful subject, but at the same time, we have to recognize its limitations, meaning that it's a linear model, it's a model that is trying to explain a particular relationship, cause effect, and it doesn't recognize the complexities of this dynamic system, right? So, I don't want to discourage you to learn econometrics. On the contrary, you must completely dominate this subject, but do not stop there. You have to move on. You have to learn things beyond econometrics and statistics. What are these things? Well, let's look at what many of the people applying math successfully in the financial markets use, and let's try to see if that makes sense. So what are some of the leaders applying mathematics in financial markets? Well, you may have heard of these firms. Renaissance Technologies, 2 Sigma, D. Shaw, TGS, Winton, and many, many other firms that you have never heard of because they don't want you to know about them. They just manage internal funds. They manage the wealth of some individual, and they don't need anybody to know. They actually run away from any sort of publicity. The ones you hear about are the ones that are raising funds, and they want you to know about it because it's part of their mission. But there are plenty of firms using math that they are just not publicly known. So what is common among these firms is that, in fact, they are mostly populated by people who are very strong in math, engineering, technology, and they are not ideologues, right? They are not they are not thinking in terms of theories that explain the markets, and these theories are kind of adopted by a large majority of people. No, they will come up with their own theories and they will test them, and they really work like laboratories. They work like financial laboratories. They will have some capital put aside to test their own hypotheses and learn what actually works in the markets. Yes?
I think I'm missing a key possible fourth explanation. Maybe it's not the ambitions of the academic economists to make money and become billionaire. You assume that they want to do that. Who knows? Maybe they are happy with the social impact they have through publications. They are more concerned with social surplus, stability of the system, and first make sure that they wanted to do that on stage before jumping to that.
Okay, yeah, it's an interesting point. So essentially the argument would be that these people are just not greedy, and even though they know the truth, they don't want to profit from it.
Well, no, maybe they see a different mission for them. They are not there as traders or trading algorithms.
Yeah.
They are different kind of people for different reasons.
So that's a possibility. I would argue that even in that case, someone should be able to make money out of these theories.
But I would argue if that's the case against this, because then that does explain why a salary for a business school professor is $250,000, and at the same time the salary for a math professor is about $90,000.
Yeah, but then that explains that as a math professor,
you make so much money.
You have more incentive to go out and make money as a.
Yeah, let me give you an example. So think of probably one of the most popular financial theories out there would be either CAPM, APT, factor models, right? People have won the Nobel Prize in economics for those things. And yet, nobody is known for having made a fortune out of those things. There is just no CAPM billionaire. There is no APT billionaire. There is no factor model billionaire. Nobody has actually been able, maybe these models are correct, but I tend to be agnostic, since nobody has been able to monetize. So the burden of the proof is on them. These theories may be correct, but the reality is nobody has been able to make money out of those.
If that theory claim that it's for making money rather than explaining the equilibrium outcome of all nice forces that you put in the first slide, basically, maybe it's.
But this is how science works, right? The way science works is you need to prove your theory. So a physicist will go to a laboratory and will say, this is the test, and this is going to be the sword I'm going to fall on. If my theory is true, this is what you should observe. And this is the only possible explanation that my theory is true. CAPM, many people have applied CAPM and APT and factor models, Feynman French. I mean, we are talking about not one theory. We're talking about theory after theory after theory after theory, and nobody has been able to become a billionaire using them. So what I'm saying is that they may be true, but for some reason nobody has been able to demonstrate them as true. There is no evidence that it may be true, but there is no evidence that it's true. That's what I'm saying.
If what Professor Guiducci said is true and does show some sort of proof that happens, how would you edit or rearrange your theory to fit that?
Well, there is a need for a specific proof that there is just no evidence that these theories work. Tell me one financial theory. Tell me one.
Why are you using it if there's no proof that it's working? I'm just trying to understand. Is there flexibility to the fact that there are these other variables?
I don't use financial theories.
Could pull the seams from the backbone of your argument.
So the backbone of my argument is that financial theory, nobody has been able to monetize on financial theories. There is just not one person who has been able to monetize on financial theories. But there are plenty of mathematicians that have become billionaires.
Well, education. Isn't that something that has profited
off
of financial theory? We wouldn't be here.
They have become billionaires because they have applied math to the financial markets. And yet there are many people out there trying to apply financial theory, and at least so far, not a single one has been able to monetize. And by the way, let me add this argument. There are tens of thousands. Most people who study finance end up practicing finance. Very few people who study math end up practicing finance in relative terms. And yet, every single billionaire who has applied, the examples tend to be that the billionaires are those who applied math. Right? We are talking about these individuals and more. Right? It's like there is just not one. At least if we had at least one person who has become a billionaire by applying financial theory, there would be at least some sort of evidence, but all the evidence is on the contrary. So that's why the greed argument does not make a lot of sense to me, because for mathematicians are probably even less greedy, in the sense that they are more interested typically in proving some very obscure theorem, in many cases without any sort of application, and yet you have many people who have become very wealthy applying math. All right, so what sort of math? Well, the sort of math that many of the firms apply is graph theory, topology, discrete math. So in these subjects, what is the key? The key is to understand complexity. Right? Graph theory is trying to understand what are the hierarchical relationships between agents, financial instruments, markets. And this notion of hierarchy is missing in linear algebra. That's one of the key aspects that I would like you to understand. When you apply linear algebra, you are interested in understanding relationships, linear relationships between two vector spaces. And that's a very limited tool. It's a tool that does not recognize the existence of hierarchies. So for instance, when you are investing in stocks, very often you are interested in understanding what are the sectors, industries, subsectors. These are hierarchical relationships, right? Practitioners use hierarchical relationships all the time. When they try to allocate assets to a portfolio, they will think in terms of industries, sectors, countries, currencies, economic blocks. They are already using hierarchical relationships. However, linear algebra does not recognize hierarchical relationships. It is not part of, it's not how, it predates topology, that's what I'm saying. Topology is the mathematical subject that deals with hierarchical relationships. Discrete math is also very interesting, very important. The reason is because it has some numerical properties that are useful in practice. Discrete math models tend to be very robust, for one thing. And why is robustness important in financial markets? Well, because it saves you money in terms of transaction costs, and it allows the model to be estimated in an accurate way. Yes?
What is the role of topology in the middle?
Topology is important because topology allows you to understand what is the organization of a system subject to a number of perturbations. The key point of topology is to understand what are the essential properties of an object that even when you stretch it, when you turn it, when you modify it, these properties still remain, right? And topology is used in a variety of contexts in financial markets. Perhaps it's not a perfect example, but perhaps the best way to understand how topology is used in financial markets would be think about a network, right? What is the topology of the network? What is the centrality of the network? What is the dimensionality? What is the density of the network? What are the points?
So what do you mean by the network?
In a network of the market is a network, right? Is a network of participants trading with each other. And so one of the questions I was asked once at the lab was, what is the one stock that a financial terrorist would try to bring down in order to bring the market down? So that's the kind of question that topology would solve for you rather than linear algebra, right? What is the centrality? What is the one stock that if someone would hack this market, it would bring the market down?
And here you mean set point topology. You mean, is that right? Or?
Yeah, topology in the sense of what are the properties of the market? What is the organization of the market?
I understand.
What is the organization of the market? What are the properties of the market that are preserved after a number of transformations, after a series of transformations?
So you look at this market as a graph, and then you try to find out, put a topology on top of that graph.
Yes.
And okay.
So, for instance, what is the minimum spanning tree of this graph? Let's say that you need to compute a tracking portfolio. Many people would use a linear regression, and it's one possible way of computing a tracking portfolio, right? Another way, perhaps better, is to understand what is the minimum spanning tree of the market. What are the axes of the market that are truly essential in order to understand its dynamics? But this is only the beginning. There are many other subjects that are important, like information theory and signal processing. After all, financial markets are all about exchanging information. Information theory appears in a number of market microstructure problems, but it's not fully exploited. Very often what happens is people deal with information, with market microstructure problems from an econometrics perspective, which is okay, but again, it's not going to hammer the problem. In order to really hammer the problem, you need to understand what is the entropy of the system. You need to understand what is the information value of the observations you are dealing with. And unfortunately, in economics, economists tend to abhor and be very much against information theory since at least the 1979, when Samuelson essentially denounced the attempts of several people in the information theory, let's say information theory school, to explain markets. And ever since it has been like you try to publish a paper that applies information theory to financial markets, and more likely you're going to be turned down in the major journals. It's kind of, it has become something very dogmatic. You know, journals, you probably are familiar with it. I sit at the board of several, but typically they are very reactionary. They don't like, it's kind of paradoxical, because you would think that journals are interested in publishing new ideas, but on the contrary, they always try to shoot down any new idea, because new ideas are dangerous, are risky. The big subject today when you have to model financial markets is machine learning. For one thing, because the market is in itself a learning machine. And I could spend days talking about how machine learning can be used in the markets, and is currently used in the markets. Let me just point to one very particular result. There is a very interesting paper that appeared in the Review of Financial Studies in the year 2009, De Miguel and others. And they made the following shocking discovery: that the performance out of sample of an investment portfolio that allocates assets 1/n, so you have n assets and you just give let's say 10 assets, you give 10% to each, the out-of-sample performance of that portfolio is better than the performance of any known portfolio optimization technique, including Nobel Prize award-winning Markovich portfolio optimization. Think of it. What it means is that when you use all these calculus and linear algebra and you optimize a portfolio and you're incorporating information about the expected returns, the covariance matrix, actually this information is not only useless, it's in fact detrimental. Because just 1 over n would be better. 1 over n, which is naive in the sense that it uses absolutely no information about the covariance matrix, no information about the expected returns, and yet 1 over n beats every portfolio optimization technique. Now, this result is not only relevant in the context of portfolio optimization, it's relevant in every context where you use linear algebra, because the reason why portfolio optimization fails is because the covariance matrix tends to be very unstable, and when you invert the covariance matrix, you are actually maximizing errors. So this is a very bad omen for a lot of people who are trying to apply, factor models and all the things in financial markets, because and by the way, it's the explanation why actually it provides a mathematical explanation why nobody has been able to monetize on CAPM, APT, Fama French, all these things. Why? Because of a numerical problem. There is a mathematical numerical instability problem. The covariance matrix, any useful covariance matrix happens to have a very high condition number, which means that even very small estimation errors are going to more than offset the benefits of portfolio optimization. Now, there are a number of techniques that you can use that apply machine learning that do not require the properties that are typical in convex optimization, and those have been shown to beat 1 over n. So it is not that 1 over n is unbeatable. It's just that portfolio optimization is so bad that cannot beat 1 over n. But there are some very simple machine learning techniques that in fact beat 1 over n by a factor of something like double performance. All right, parallel processing, quantum supercomputing. We said before, financial markets are really, really complicated systems. And we have no hope of modeling financial markets with a small machinery. I mean, we can learn, but in order to actually go and manage money, we need supercomputers. We need to be able to simulate tons of paths. We need petaflops of computing power. Why? Because if forecasting weather is simple and it requires petaflops, well, financial markets are more complicated, and definitely we will need supercomputers. Quantum supercomputers, in fact, quantum computers are today reality. They were not a reality a couple of years ago, but now they are reality. The D-Wave machine already has 2,000 qubits and has been shown to be able to solve problems that are NP complete, among the hardest problems in complexity theory. Experimental techniques, and this is a topic I'm very passionate about. What is experimental math? Experimental math is applying physical arguments to math. So let me give you an example. Suppose that you are Andrew Wiles. Maybe you have heard about him. He spent 5 years of his life trying to prove Fermat's last theorem. And after 5 years, he actually came up with a proof that happened to be wrong. He was desperate. He spent another year trying to fix his proof, and eventually he fixed it with a friend, with the help of a colleague. But it was really, really close to become a blunder. His proof is very complicated. It's hundreds of pages. Nobody could understand his proof. So actually, it was kind of a miracle that someone was able to identify an error in his proof. We are at the point in math where our proofs are so complicated that nobody can understand these proofs, only the person who originated the proof, which means that there are many proofs out there that may be flawed. Now, that's where experimental math comes in. Experimental math treats mathematical objects as if they were physical objects. And you're going to bombard this object with a number of trials and tests and experiments in order to understand the properties of this mathematical object. So essentially, experimental math is a way of telling Andrew Wiles, we don't really care about your proof. I mean, it's good that you have a proof, but the reality is we cannot wait for 300 years or 265 years between the death of Fermat and Andrew Wiles. I mean, we cannot wait 265 years for a proof. It's much better if, in the meantime, we use our time to conduct some experiments with these mathematical objects and understand what these objects are about. What are the properties of these objects? What can you do and you cannot do with these objects? What sort of properties do they exhibit? And that's what two of my colleagues did many years ago, Borwin and Bailey. They came up, actually, you may not have heard of them, but in fact, in the 90s, they became so famous that even they appear in The Simpsons. What these guys did is they came up with an algorithm to estimate any decimal of pi in any position. So for instance, their algorithm can give you what is the 1 millionth decimal point, decimal position of pi without having to compute the previous ones. It just gives you that particular one and all the rest until you ask the algorithm to stop. And how did they come up with this formula, what is called the Plov-Bailey-Borwin formula? You can search for it in Wikipedia, it's very famous. They achieved what nobody thought it was possible. They used, back in the 80s, I guess, a computer to come up with an algebraic formula that would match pi. So this is a formula that nobody understands, and yet it works. It works. It can give you any decimal point, any decimal position of pi without having to compute the previous ones. And again, this formula is not the result of a proof. It's not the result of a theorem. It's a result of understanding what are the experimental properties of the generating function of pi. So research, financial research, economic research is in fact in a crisis. The crisis is that there are plenty of papers out there, there are plenty of theories out there, and really nothing seems to work. And yet, we have to be able to use something, right? And really the solution to the crisis is in you, right? What you have to do, or what I would advise you to do once you are in the market, is to not be dogmatic and assume that everything you have learned is useful, but not necessarily correct. And just try many things and see what sticks, see what works. Thank you very much.
I think we have a few minutes for questions, if anybody has a comment.
Thank you very much. So my argument, thank you, is not against your argument that we need more math, of course. But my argument is on the title of your talk. Making money, trading, etc. is a very, very narrow subset of science of economics. We have labor economists, we have health economists, we have energy economists, environmental. None of them would have any single ambition to make money, and none of those theories are meant to make money. Of course, you're saying the theory should could test the data. Of course, I agree with you, but making money was not the mission of that theory. So why the theory which meant to increase the stability, to improve the performance of the auction, or frequency, etc., why they should come and compete in a game which they are not interested in?
All right, let me. I understand the point, and it's a valid point. Let me counter argue it, but at the same time that I acknowledge that you are partly correct. It is true that there are many areas in economics that do not that do not aspire. They do not try to monetize some particular law, and yet, as a scientist, you need to ask for a test, right? It cannot be that because the purpose of the law is not to make money, that we are not going to ask for a benchmark. So we need the benchmark. Right? So for instance, if you are, let's say that you and I, we work together on a law of labor economics, someone must be able to monetize something. It's economics after all. There must be some way, either the employer or the employee or the society as a whole, there must be some way to monetize, to compute in economic terms, what is the value of that. The same, look, that's what I say. And in particular in finance, there is no excuse.
Even I would argue, another part of finance is money making. Let's say you're working on risk management, right?
Oh yeah, you have to monetize risk.
No, you don't have direct money making. You give advice, you're happy that after people adopting your theories, the entire financial system is in a higher level of stability. Of course, the society has benefited, but it doesn't mean that you can benefit on that. It's just you propagate these theories and the efficiency of market is higher, but it's a highly distributed benefit to everybody. And you enjoy seeing that the markets are working in a more efficient way because of your theory.
I would counter-argue that in finance there is
that's
no.
What I would suggest from economics perspective.
Yeah, but
we are aiming. We are never dreaming of making money or going towards.
No, but the reality, even if you are not dreaming about making money, your theory needs to be able to make money because it's economics. It's economics, it's finance. It must make money. It is what it is. It is what it. Look, it's like coming up with a model for winning in poker, but you're not interested in making money. No, it's poker. You have to make money, and even if you're not interested in money, still someone must be able to monetize it because it's poker. And the same with economics. There must either your theory must be able to have an impact on the GDP, it must be able to have an impact on inflation, on something. It must be able to be measured in dollar terms.
But not on your private debt.
We have one more here.
Yeah, but someone, not you, but someone must be able to.
We have one more question.
Yes, go ahead.
When you joined your talk, and I'm not an economist or I don't have anything to do with finance, I'm a mathematician.
Mm-hmm.
So from the point of mathematics, I have 2 points
Yep.
that I need to ask. One is that if somebody from math discovers something in the finance, they wouldn't probably say so, and they would make money out of it.
Yeah.
So probably publication on those cannot be trusted to be accurate. Is that right?
I think that's quite right. Meaning that when someone publishes in particular investment strategy, either the strategy is not going to work anymore, or it never worked in the first place. Right? If it works, it will cease to work.
So the subject that you discussed probably could be outdated right now.
Well, I didn't discuss an investment strategy. I discuss methodologies that you can use in order to develop investment strategies, machine learning, etc. Yes.
So another point is on the experimental math,
Yes.
which we don't have anything like that.
Yeah.
In mathematics, either you have the proof for
Yes.
something, or that thing is not right.
Yeah.
Okay. So
True, actually.
yeah, true.
It's not true. There is
No, but-
proof using computers.
So-
in your own areas, by the way, in your own department. The math department here, Steve, they do proofs using computers.
It is. Let me.
That was my point.
Yeah.
That you don't need experiments. So for
No. Let me. The point here is that I agree completely with you that following the classic Greek paradigm that has worked really, really well for 2,500 years, there must be a proof. There must be a theorem, and the proof is airtight. There is no. This will be true until the end of the universe, right? Pythagoras' theorem has been proven. I think there are something like 300 proofs of Pythagoras' theorem. It will always be true. This is a fact that will never change.
Okay,
And
I
yet-
think we're going to have to stop, and thank you everyone for coming. Let's give them a round of applause.